Hello everyone and welcome to my lecture series on molecular docking. And today we would talk some more detailed aspect of molecular docking and virtual screening. Okay, so let me give you a brief idea as to what we would be doing and what I have already covered up so far. Okay, so there are multiple steps that are needed to be followed when you perform molecular docking and virtual screening. Okay, so the very first step that you might begin would be to uh, create a compound library. Okay, so we have already talked about this aspect. I have already mentioned as to there are I have mentioned you that there are four methods, easy methods that you can use for creating your compound library. So we have already dealt with this aspect. So if you have not seen those video, I would recommend you to see these videos first before you proceed with this demonstration. The second step would be to uh, obtain and prepare a target protein. Okay, so in our case we are going to use target COX-2, which is cyclooxygenase 2, and this enzyme is involved in evoking and maintaining your anti-inflammatory response. Okay, so this is going to be our target molecule. So third thing that we need to do is, of course, validate your system and then perform molecular docking and virtual screening. Okay, so after you finish off with validation followed by molecular docking and virtual screening, you would have to generate complexes of your ligand and protein system. Fifth step that you might do after generating the complex would be to perform interaction analysis. And the final or the sixth step that we will be talking about is to create publication quality images. Okay, so we have used different software in creating compound library. I have told you as to how you can use CameDraw, right? Then we have also used OpenBabel. We have used online resources like PubChem Compound, okay, databases on NCBI, right? So on and so forth. So for the sake of obtaining and preparing the target protein, well, for obtaining the target protein, to obtain the structure of this target protein, we would be using PDB website, PDB database, which stores information on protein structures. And for preparing the target, we would be using softwares like Swiss PDB Viewer, and the rest of the processing would be done in Python prescription. Okay, and for this validation of the system, MD simulation and virtual screening, we would be using Autodoc. Okay, and we would be running this Autodoc through the interface called as Python prescription, right? For generating the complexes of your protein ligand system, we would be using a lot of softwares that would include OpenBabel. Of course, we would require open Babel. Here we would be using TextPad or any text editor if you have for editing the uh, protein ligand complexes. Okay, and for performing interaction analysis we would be using like plot plus. Okay, and to create publication quality images I will demonstrate how to do that using PyMod. Okay, so these are the softwares that I intend to use during all of my all of my procedures that I am going to tell you. So we have already finished up with this. Well, now let us focus on this video as to what are the steps that are needed to be done when you how do you obtain your protein data bank file for your target protein, and how do you prepare it, what are the steps that are needed to be done. Okay, so let us focus on this task for time being. Okay, so to begin with, let us begin with, of course, go to open your favorite browser, uh, open your Google, and then search for PDB. And after after clicking on the very first link, you might end up on this PDB web page. Okay, so the PDB ID for the COX molecule that I have already mentioned you, the target protein that we are going to use is 3NT1. I already know the PDB ID. Okay, so if I search for this PDB ID 3NT1, you might come to this particular entry page of this molecule, high resolution structure of naproxen in complex with COX-2. Right, naproxen is one of the very famous inhibitor of cyclooxygenase 2, and we are going to use this complex as a starting point for our molecular docking and virtual screening. Right, so when you want to download any file, of course you have to use this drop down menu and click on this download files in PDB format. Okay, it would ask you what is needed to be done. We want to save it. Okay, and when you hit OK, it would be saved in your downloads folder. Right, so you can check it out over here. This is the molecule that I have saved. So I have already done this task of saving. Well, let us now begin to visualize our COX-2 protein molecule and check if there are some things that are needed to be done before we proceed to virtual screening. Right, so well, let us first start out visualizing your protein molecule. Okay, so this is 3NT1 molecule that I have downloaded. This is the complex of cyclooxygenase 2 and naproxen. Now for visualization I usually prefer this SPDB, Swiss PDB Weaver. Okay, what I can do is that I can drag and drop this molecule into our Swiss PDB Weaver. Want we don't have to worry about this general communication. Okay, so we also don't want this log file. Okay, so as you can see, this is a beautiful three-dimensional image of this naproxen in complex with cyclooxygenase enzyme. Okay, so basically this particular entry of naproxen in complex with cyclooxygenase, well, it is in the dimeric form of this enzyme COX. So maybe if I color it by chain, yes, you can see that there are two chains, chain A which is shown in yellow color and chain B which is shown in blue color. We also know that this cyclooxygenase enzyme can also function if it is even present in its monomeric form. right? So even so if we remove the remaining B chain, then also our enzyme would be functionally active. Moreover, we are planning to use the same PDB structure that we are going to use in molecular docking in our subsequent molecular dynamic simulation analysis. So it would be better that we reduce the number of atom right now, right? So what I will do is that I would again color it by CPK, right? And I would select only chain A. As you can see, if I click on this chain A, I would select the entire chain A, and chain B is not selected. Okay, what we are trying to do is to separate the chain A from this dimer, and we would separate this chain A into a separate file. We would save it into a separate file. To do so, what you need to do is to first select the entire chain that you are supposed to save, then go to file, then go to save, and select selected residue of current layer. So what we are doing is that whatever we have selected, we are going to save it into some separate file. Okay, so we would go to this docking lecture, our second task. Okay, and I would save it as 3NT1 3NT1 chain A. Okay, let me save it. Okay, now we don't need this dimer anymore, so I would close it. Okay, one more thing that you should always do is to make sure that whatever you have saved, let us check it out if it is properly organized or not, right? So let me open this newly formed file. This 3NT1 chain A now only contains a single chain, right? So let me first check it out in its text editor if everything is all right. So let me go scroll to the very down, and as you can see, since we have used spdbv to separate this chain, it appends some lines of its own when you try to save the molecule. I don't know if it is a bug in their software, or it is just a normal procedure, but these lines usually pop up when you perform some action of saving the file separately into using spdbv. Okay, so since we are planning to use subsequent software like even GROMACS or NAMD for molecular dynamics, and these softwares are very picky about their inputs. So it is always better that you don't have any unnecessary or some doubtful lines to be present in your PDB file that might further create some problem in your analysis. So it is better to keep all the conventional lines with the keywords that are already familiar for that software, for the software that you are going to subsequently use. Okay, so all in all, we don't want that lines that begin with spdbv. So now let me tell you as to, let me save it first. Okay, file, save. I have already saved it by pushing this Ctrl S button. Okay, so let me tell you as to why what was the function of those lines, spdbv lines, in your protein file. So these lines, were responsible for maintaining the orientation of this chain with respect to the dimer. Okay, and since we are only working on the monomer, we usually will not need the orientation with respect to the orientation with respect to the remaining monomer that is missing. So even though if we remove those spdbv line, it won't matter much. So that is why it is better that I have removed it. Okay, so I have saved it, and let me save it. Okay, now let us try to visualize this thing. 3NT1 chain A. Okay, now you can scroll down in your control panel and see that there is no chain B in your protein molecule, there is only chain A. Okay, so file, close this. This is what we are supposed to check out. In control panel, right? So it also contain only chain A with its prosthetic group. There are certain prosthetic groups that are also present in your protein molecule, right? So let me show you what prosthetic groups are there so that you can also visualize them, and you can determine as to where they are present, right? So this particular chain A is in complex with its inhibitor naproxen, that you can see it is present in this lines representation. This is your inhibitor, okay, and it is also co-crystallized with its cofactor heme, right? So here we go, here is the heme molecule, and as you can see that this heme molecule is not part of the binding site where your substrate or where your inhibitor might go and bind. Okay, so it is located quite far away from the ligand binding site or active site of your protein, as you can clearly see. Therefore it is completely dependent on you if you want to retain such prosthetic group when you proceed for molecular docking or virtual screen. You should also always consider these things as to what things in your model are essential, so that you can find the answer to the question. Okay, so it is always advised that you don't retain things that you don't need for the molecular docking or molecular dynamics purpose. Okay, so since heme has got a very trivial role to play, so far the inhibition of so far detection of binding site and interaction analysis is needed to be done. Therefore you can conveniently remove this heme atom from your protein molecule, right? But if it happens that if you are working on say some different protein, and if the prosthetic group also binds to the same place as your inhibitor or substrate bind, then you might want to retain the prosthetic group as well as the inhibitor in your docking study. Okay, so in our case, since heme do not directly interact with our substrate or our inhibitor molecule, even if we remove it, that will not make much of any difference, right? Because the binding sites are completely different. Okay, so the binding sites are not overlapping, as you can see over here. Okay, so what we would do is that we would only retain this naproxen, okay, and we would remove all the unnecessary, for time being we can call them as unnecessary cofactors or other non-protein component as such. Okay, so now let us select all the non-protein component. Okay, so here are all the non-protein component, which starts out with this NAG residue. Okay, and once I select all those non-protein component, I would go to select and then use this inverse selection option. So what this inverse selection do is that it would select everything other than what was selected in your previous step. So in this way, I have now selected only the protein portion of cyclooxygenase 2 chain A. Okay, and now I will save this into a separate file. Now this new file will not contain any prosthetic group, and we can call it as an apoform of your enzyme. Okay, so for doing that, once you have selected only the protein portion, then go to file, then go to save, right, and then go to selected residue of current layer. Okay, and then you can rename it as apoform of 3NT1 chain A. Okay, and then save it. As I have already done it, it is asking me if you want to replace it. I would say yes, and thus we have created apoform of 3NT1 which has got only chain A. Okay, so let me again edit it by removing those SPDBV lines that might have appeared at the end of your file, right? So it has appeared over here, we don't really want them, therefore let me remove it. Again save the file. So this is your apoform which will not contain any prosthetic group or inhibitor group. So this is it, and what we need is that for validation purpose we would need this naproxen molecule. So we need to save this naproxen molecule as well into a separate file. So what I have done is that I have clicked on it so that it becomes red, that would indicate that it has been selected now. Then again go to file, again go to save, and then use this option, selected residue of current layer. Okay, and I would name it as NPS. Okay, and then again save it. Since I have already done it, so it is asking me do you want to replace it. I would say yes. If you have not done it, or if you have begun doing this thing, then there would be no file name NPS in your folder. Okay, so I would just replace it. Okay, so what I have done now, I have now separated the inhibitor group from your chain A and saved it separately. So since I have used SPDBV for this separation purpose, again I would have to edit this file and remove those SPDBV lines that might have appeared at the end of your PDB file. Okay, I have selected it and I have deleted it. Okay, I will save it. So you can use any editor for this purpose. Okay, it is not necessary that you use TextPad. You can use any editor for this thing. Okay, so here we go. We have now the apoform of your molecule. I would close these things now. Okay, we have the apoform of your cyclooxygenase 2 which do not contain any inhibitor. Okay, you can check out at the end of your amino acid residue list that there are none of the prosthetic group or inhibitor group or hetero group that are listed over here, right? And we have separated our ligand molecule. Here we have, I am loading it once more, right? And we have loaded it in some different layer, so you can see that you have got this NPS. Okay, using this control tab you can see that there are two layers. First layer is your protein molecule which don't contain any ligand, and we have separately loaded another layer of our NPS. Okay, I will just show you. So although it appears that the ligand is placed in your protein molecule, but since we have retained the coordinate of the ligand and the protein, it is kind of appearing that it is still present in the protein. But in fact, as you can see that these are two separate molecules that we have saved. Okay, good. So this is the elementary thing that you have done. So what I want to convey you from this particular exercise is that you should always consider as to what portion of your protein molecule do you need to retain in your file when you prepare your target molecule. Okay, if it is indeed necessary for its activity or for its inhibition, then you have to retain all those non-protein component in your protein, and if they do not play much role in your inhibition or in your molecular docking, then it would be better if you remove them. So it would be completely dependent on you as to what is your objective or what is the question that you are supposed to answer, right? And for this case, for this purpose, we no longer need that prosthetic group. In our case, it was a molecule. It would be enough if we have our ligand molecule and we have our protein molecule. Okay, I hope I have made things very clear now. So let me close this. So this is one part of your preparing the target molecule, downloading your target molecule from PDB, and then deciding as to what things you might want to retain in your PDB file and what things you might want to delete. Okay, do these things very smartly, because that is what is going to affect your further course of writing and further course of analysis. Okay, so let us assume that now we don't need other prosthetic group and we are happy with our inhibitor and the protein molecule as such. Okay, so now let us begin our discussion, or let us begin our discussion to the next level, right? So we have also done with this thing, right? Now let us talk about what is validating your system and how do you perform molecular docking and virtual screening, right? So for this purpose, as I have already mentioned you, we would be using this software called as Autodock. This Autodock is a software that is going to be run in the background, and we will be using this Python prescription user interface to run Autodock in the background. Okay, so Python prescription is a graphical user interface, while Autodock is the software that we would be running using this graphical user interface, GUI, what we call it as. Okay, so let us begin our molecular docking. First, let me show you around as to what exactly this Python prescription software would look like. Okay, so when you double click this Python prescription icon on your desktop, you might end up with this screen that might that is how your Python prescription looks like when you open it for the first time, right? So if you are wondering as to how, from where do I get this Python prescription and how do I install it and how do I configure it, I would advise you to see my previous video in which I have already described as to how do you install this software and what are its dependencies and how do you configure it before you proceed for molecular docking. So if you have not seen those video, I would advise you to go through them as well and then come back to this video. Okay, so now let me assume that you are already familiar as to how do you install it and how do you configure it, right? So this is how your Python prescription software would look like when you load it for the first time. Let me maximize it, and I would just walk you through as to what are different components that are present in your Python prescription software or GUI. So over here, this is called as the navigator panel. Okay, and in this navigator panel, there are 4 tabs, of which 2 are of our utmost interest, what we call it as the molecule tab and what we call it as the autodoc tab. This molecule tab is the one in which you would be loading your molecule, and autodoc tab would let you know as to how many ligands are there that you have loaded and how many targets are there that you have selected for performing molecular docking. Okay, this view panel, you can visualize your target molecule and your ligand molecule in 3 dimension. All the visualization stuff would be done over here. And of course, another important tab in this view panel is this table. This table tab gives you option for displaying how many ligands are there, how many targets are there, and it would also show you the results. Okay, and there is option for saving saving your results in separate comma separated value, or you can even plot those, right? Or you can open the comma separated values if you have already, I mean, if you want to visualize or if you want to see what you have done earlier, you can also load those comma separated resulting values. So these are the two main tabs that we are going to work, right? And the next third and most important component of your Python prescription is this control tab. This is where you would be controlling if you want to use Autodoc Vina, or if you want to use Autodoc Wizard, or if you want to use OpenBabel, right? I have already shown you as to how this OpenBabel work, and we are going to use this particular component today as well for demonstrating your molecular docking. Okay, so for this purpose we are not going to use Vina, we would be using Autodoc Wizard. And if you click on Autodoc Wizard, you can see that there are separate 5 sub tabs or sub menus that appear over here, right? I will tell you in just in a while as to what and how do all these things function, right? So this is how things are, you know, organized in your Python prescription graphical user interface. And this being a Windows software, of course there are menus like file, edit, view and help. You can explore them in more details. And besides this main menu, there are certain shortcuts present over here, and we are going to use one of these shortcuts. Like I would show you as to how do you use this load docking log file further in our next tutorial. Okay, so all I want to show now is that these are the things that are present in your software, and I will show you as to when and how do we use it, right? So first let us begin by loading whatever target that we have prepared. Okay, so for that what you are supposed to do is that go to this file and then use this load molecule command, right? And browse to the location where all your files are located, right? We'll go to this docking lecture, then validation, then this is the final structure that we have generated, apo 3NT1 chain A. That is the file that would contain only the chain A of cyclooxygenase enzyme without inhibitor. So this is what we need. We would open it, and now you can see that you can visualize your molecule in 3 dimension over here in your view panel, right? Similarly, we would also need our naproxen molecule that we are going to use for validation. Okay, now you can see that there are 2 molecules, and you can also see that the inhibitor that we have loaded later on, our naproxen, it is present in ball and sticks representation, while your protein molecule is represented in lines representation over here. Okay, so we have loaded our protein molecule and ligand molecule. Next thing that you need to do is that your protein molecule and your ligand molecule is still in PDB format, but Autodoc needs the input molecules in say PDBQT format. So PDBQT format is the same as PDB format, but some charges are assigned. Some hydrogen or hydrogen molecules are added in it. And now you can see that over here you don't see any hydrogen molecule. And when we further proceed for processing our target, and what we need to do is to convert your PDB format molecule into PDBQT format molecule, so that your Autodock would be able to recognize it as its input. Okay, and for doing that, all you need to do is to right click on it and then use this Autodock menu, and make sure that you are selecting the protein molecule. Okay, right click on this protein molecule, use this Autodock, and you can make it as a macromolecule. Okay, and after making it, when you hit this make macromolecule command, what it will do is that it would convert your PDB file into PDB QT format file. And now you see that there are no hydrogen atoms present over here, but when you convert it into PDB QT format, you would see that hydrogen atoms would appear here in cyan color, or in, say, you can say it as light blue color. Let me show you. So in background it is kind of running OpenBabel and converting your PDB file into PDBQT file, and now you can see that there are these hydrogen molecules that are optimally added to your protein molecule, and you would also see that a new folder has appeared over here in macromolecule section. Okay, and this ligand section, if you double click it, it is still empty. Okay, so we would do the same thing by converting our ligand molecule as well into PDBQT format. For this, all you have to do is to right click it, select Autodock, and make a ligand. Okay, and now in Autodock you can see that nps.pdbqt file has appeared over here, that was not present earlier, and they are in PDBQT format. Okay, you can open this as well, and you can see that your protein molecule is also now being converted into PDBQT format. Okay, so this is how you process your protein molecule and ligand molecule for using it as an input to Autodock. There is one more thing that we are supposed to do, is to load your compound library. And to load your compound library, what you can do is that you can use this Open Babel tab over here. In this Open Babel tab, what you can do is that you can go over here, use this insert new atom command. Okay, and then go to the file where your compound library is located. Okay, so it is the same SDF file, it is the same compound library that I have created in our previous lecture. I would select it and I would open it. Now you can see that the compound library has been loaded. Okay, but these are all files in SDF format, and if you want to use it in Autodock, we would need them in PDBQT format, right? So what I will do is that it is always advised that you minimize your compound library first if there are any uh, I mean if there are molecules in its unminimized state. To do that, you usually right click it and then select minimize all, or you can use minimize selected as well. Okay, if you minimize all the atoms that are all the molecules that are present in your compound library would be uh, minimized for one after another, right? And now you can see that there is a single inhibitor present over here. Now if I again right click over here and use this convert all to Autodock ligand, all of the molecule that are currently present in SDF format would be converted into PDBQT format. Okay, so this is how you do. Right click, convert all to Autodock ligand PDBQT. Select it. Now you can see that this list has been updated one after another, right? And now you can see that there are a lot of ligands that are loaded over here. Okay, so now our system is ready. You have our protein molecule in PDBQT format that your Autodoc can understand, and you have the set of ligands that you wish to dock into your protein molecule that are also present in PDBQT format, right? So let us begin our virtual screening and Autodoc, or you can say molecular docking procedure. As I have already mentioned you, I would be using this Autodoc and not Autodoc Vina. If you are interested in doing molecular docking using Vina, you would have to use this Vina wizard. For this practical purpose, I would be using Autodoc wizard, right? And when you select this menu, Autodoc wizard, by default start here is the default tab that is active. Okay, and now make sure that you push the start button so that your software would know that you are using Autodoc. Okay, so make sure that you push the start button first, right? Then the control would automatically go over to the next tab. Okay, so now in the current position it says that you have selected a single ligand. That is not what we want to do. We want to dock all of the ligands that we have created. Therefore what you can do is that you can select the first molecule in your list, then con- uh, then uh, then press the shift button on your keyboard, and then press the last one in your list, so that now you can see that all the 17 ligands are selected. Okay, and if you have not selected this PDBQT format in format molecule in macromolecule folder, then make sure you do that. But it says that it has already selected. Now just make sure that before proceeding you have selected all the ligands that you need for docking, and you have selected the right PDBQT file that you wish to use as a target molecule, right? So after making sure that you have selected everything, then all you have to do is to hit forward, so that your system would be ready to run this autograde command. Okay, so now the control has been forwarded to the next step, that is to run this autograde. And mind you my friend, this is one of the most critical step in molecular docking, right? So by default your grid center would be set to the center of your molecule. Okay, and it is not necessary that the active site or the binding site of your ligand is always at the center of your protein molecule. You would have to shift your grid box so that you can perform docking. So if you proceed this way and click forward, then the grid would be set at the center of your box while your active site would be somewhere else. You really don't want to do that. Okay, so always make sure that you place your grid box at the place where the binding site is. Okay, so so in this case we want to shift our grid from the center of molecule to the site where your ligand is supposed to be binding. And since we have the crystal structure of our protein ligand complex, we already know that this is where our ligand molecule would go and bind, and we would place our grid over the ligand. That means we are placing our grid in the active site of your protein, right? And therefore my friends, I would advise you to start out with a protein molecule that is already co-crystallized with ligand or substrate, so that you don't have to find out as to where the active site is. So if it is co-crystallized with inhibitor, that means you already know where the active site is, and all you have to do is to place the center of your grid around that inhibitor, so that you would have placed it appropriately. And what do this grid box means? So this grid box means that uh, this would be the space in which the molecular docking would be performed. Okay, so like you are telling your autodock, okay, I want to dock my ligand only in this particular area, only in this particular volume. Okay, and you should also note that I am, you know, I am moving this grid box using this central atom. So don't mess around with the remaining. It would change the size of your grid box. Okay, and you want to keep the dimension of grid box to x, y and z value of 50 50 50 50 50 50 points grid box is to be maintained, so that it would be convenient for others to reproduce your result. If you go on messing with the size of the box, it won't be, a very good idea. And while the review process of your paper is on, they won't get the same results and you might end up in problem. The reviewer might not get the same results. So, and the best policy or a good quality scientific work is the one in which the results can be reproduced. Okay, so for the sake of reproducibility, well, let us not mess up with the other dimension. You can change it, but let us not do that. Okay, and when you hit this forward button, auto grid program will run. Now you can see that over here auto grid is running, auto grid, right? So now what we are doing is that we are generating grid files for our system. Okay, it won't take much time. It is already 62% completed. Okay, so now you can see that the it says over here successful completion of auto grid. Okay, so this is one of the step, and the control has been already transferred to autodock. Over here as well, you can check if you want to include these molecules in your subsequent analysis, or if you don't want to include the molecule. Well, we want all the molecules needed to be docked, therefore I would let these things as they are. I would proceed with things as they are, right? So make sure that everything is selected, and then just hit this forward button so that you would run this autodock command. Okay, one more thing, you can change the docking parameters using this option. By default, we would be using Lamarckian genetic algorithm. Okay, if you want to change the docking parameter, then you can use different docking algorithm over here, and for each docking algorithm you use, you can change the parameters. But for time being, I would only use the default parameters, and that is enough for our experiment. When I hit forward, your autodock will proceed for its calculation, and depending on the computational power, it would start running. Now you can see that it is docking seven molecules at the same time, right? And the status over here is showing that it is running. So it is running kind of 7 docking calculations simultaneously. Okay, and soon it finishes this calculation, it would take the remaining molecules as well into the queue as such. Okay, now you can say that the remaining molecule are in queue while it is still calculating the molecular docking calculation for the first 7 compounds. Okay, it might take some time, it might take a while. So all you have to be is to remain patient. So while you can see over here, it creates a tab for each and every molecule that you create. Okay, so this is first, this is the tab for aspiridine, this is the tab for diosmine, and if you click over here, you can see that there are different tabs for different molecules, right? And in your table, now you can see that the docking results would start to pop up over here once the calculations are finishing, right? Yes. Now you see the calculation for NPS 4 prime methoxyflavone are finished, and it is kind of, including the other molecule as well. See, now it has included myricetin in its queue. Initially it was in queue, now it is running. So in this way, one by one, it would include all of the molecules, right? Well, now let us see what is the results that we have obtained for the compounds that are complete. Now you can see that over here we know that what is the binding free energy for each and every compound for your target molecule, that is cyclooxygenases as such. Okay, let us wait for a while so that it finishes. There are only 1, 2, 3, 4 compounds remaining. So here is the binding free energy of minus 8.49, indicate that this is the binding free energy for 3 hydroxy 7 methoxyflavone when it goes and binds with your cyclooxygenase enzyme. The last few compounds are in process. Okay, you can see over here all the calculations over here are finished. Okay, the last few compounds are being calculated. It is still calculating for silibinin and naringin. Now I suppose only one is remaining. Okay, so when you finish with this autodock docking calculation, the command is already transferred to this analyze result tab, and in this analyze result tab you can see that you have got pose wise binding free energy. What pose, what is the pose, and what is the binding free energy that is associated with your the pose that has been selected or that has been calculated. Okay, we'll come to that in a while. First let me show you as to what are the results that we have obtained. Okay, so these are the results. If you go to table and use this docking results tab, open this docking result tab, you can see what are the results, and it says that the binding free energy of 2' hydroxyflavone in the cyclooxygenase enzyme is minus 7.85, while the binding free energy of the diosmine molecule is 2.31. Okay, so the binding free energy for the standard compound that we have used, the standard inhibitor, that is minus 8.83, right? So lower the binding free energy, you can consider that lower binding free energy reflects the binding affinity. So lower is the binding free energy, higher would be the affinity of that ligand towards that protein molecule. Okay, so lower the binding free energy, higher is the affinity, and better is that compound. You can consider it as a good compound or a good candidate that can go and bind to your protein molecule. That is how things are needed to be inferred. And since you might want to share your results in form of what binding free energy you have obtained, I would advise you that once you finish such docking calculation, you save this particular result in a separate comma separated value, so that you can use these values in while you present them in your research paper or in your project presentation. Okay, so all you have to do is to use this button, save as comma separated value. Okay, and let me save it as somewhere. Okay, I would save it as docking results. Okay, now you can see. Then I would also advise you to save everything into an archive, so that you don't want to do it once more if it comes to that. Okay, so you should always save your result, and in order to save the results you have to go to file and export everything that you have done in a tar.gz file. Okay, so I would just browse the location. Okay, and maybe I would rename it as Cox2, right? Okay, and when I finish, whatever we have done would be saved in an archive. Okay, in a tar archive. Just load it as finish. It would ask you, this is this the place where you want to save it? Our results would be saved in C folder, folder that is located in C drive, in a folder name user Rohan and then Cox2, right? Just remember this path so that you can locate the file where your results are saved. Okay, hit OK. Okay, now let me see. Go to your computer, then in your C drive, then open your users folder, then Rohan, right? And in this Rohan we have saved it over here. See, COX2 Pyrex Autodoc with the same date, 2012, right? 20 December 2021. I would cut it from over here and place it where all our results are there. Okay, here we go. So here are our results in spreadsheet. You can open it in Microsoft Excel. Okay, and here is the name of the inhibitor, and here are the binding free energy values, and you can tabulate it in your project report as well. Okay, and you have these things in the archive, right? You can use any zipping software, okay, and extract it to say some folder, right? And all of the results are extracted, right? So all you can see is all the results are present over here, right? We would come to this in our next lecture as to what do we do with all these results and why I have exported it and saved it separately. Okay, well, now let us talk about one important aspect that I have not mentioned. That is, we have still not discussed this issue, validating the system. Okay, well, let us first discuss it. I have shown you how do we perform molecular docking and virtual screening. But one of the main objective of performing molecular docking is to first validate your system and then go for molecular docking and virtual screening. In this case, we have validated our system as well as perform the virtual screening and molecular docking in a single step. Okay, so let us now talk about what is validation of your system and why is that you need to validate your system. Okay, so one might think that okay, this is a software, right? And we are using this software for predicting if our ligand would go and attach to this target or not. Okay, then softwares are just computer programs that have been taught to follow certain set of instructions. And then you might think, like, what are the odds that these software would give me results that are biologically relevant? Okay, how can I decide if this software is giving me right results or not, or it is just doing some calculation which are not at all biologically relevant, or which do not have any chemical significance as such? That is what I wish to ask. Okay, it is entirely possible, right? So how do we rely on the results of such software? Do we blindly believe whatever this software gives an output, right? So there must be certain mechanism by which we can access the accuracy of this software, or the mechanism through which we can test if this software is giving me right result or not, if the results that are offered to me by this software, are those results biologically meaningful or not, right? So for doing or for testing this, you need to perform validation. Okay, we say that you need to validate your system first before you proceed for molecular docking. Okay, so in validation, what we do is that we try to evaluate if your software is giving you right results or not, or if you can really rely on the results that are offered to you by your molecular docking software. Okay, and to validate, what we do is that we test the ability of our software to regenerate the experimental or crystallographic pose of your ligand. Okay, so let me just show you. Okay, so here you can see that we have got this complex of protein molecule and your ligand molecule. Okay, so for time being, just to show you how validation works, we won't require this structure of protein molecule. It is kind of uh, diverting our attention, so I would hide it. Okay, now you can see that this NPS is the crystallographic or experimental pose that we have saved separately from our protein molecule. Do you remember? The one which is blinking now. This is the crystallographic pose or experimental pose, right? And this is the predicted pose, right? So what is on view currently is the pose of your naproxen or your inhibitor that we know is going to result into productive inhibition of your enzyme. So in short, what I want to say is that if your ligand orient, if your naproxen ligand orient into the active site of protein, taking this conformation or taking this particular pose, we know that it would inhibit your protein. Okay, now what we would do is that we would test by docking the same ligand into the active site of protein using our software and see if it regenerates the same pose as the experimental pose. Okay, now what you see is the binding pose that our software has predicted. Okay, so this is the first binding pose. As you can see, I'm clicking over here, and if I hit the down arrow, it would show you what is the next binding pose. Okay, this is second binding pose it has predicted, this is the third binding pose it has predicted, and you can see that there is certain difference over here, right? This is the third, sorry, this is the fourth binding pose, fifth binding pose, sixth binding pose, seventh binding pose. Now you can see the seventh binding pose, right? The seventh binding pose, you can see that it is almost similar to the experimental or crystallographic pose. So all in all, what I want to convey is that our software is able to predict the same pose as that as in experimental setup. Okay, in short, our docking software is able to regenerate or reproduce the experimental pose. That is what we would infer from this particular experiment. Do you see? This is the experimental pose, and this is the experimental pose that is blinking, and this is the docking pose that we have predicted, right? So the docking pose and the experimental pose have been predicted in a very precise way. Therefore, we can say that we can trust this software for the poses that it has predicted for the remaining compound. And thus we say that your system is validated, right? So if your ligand can predict the experimental pose for a given inhibitor in that particular protein molecule, that means you can also rely on the poses that it has predicted for your test molecule. And now you are quite well assured that whatever poses it has predicted for your test ligand, like 2' hydroxyflavone or 3 hydroxy 7 methoxyflavone or formaldehyde or diosmine or catechin, well, you can kind of rely on the results that you have obtained. Okay, so mind you that we have performed validation as well as the testing or virtual screening at the same time, right? But usually what you do is that you first validate your system by checking if your software indeed gives you the same result as that of experimentally observed poses, and you begin with a co-crystallized protein ligand complex. Okay, so when you are sure that okay, my software is giving the same result, it is predicting the experimental pose, then you use the same setting for your grid setting and algorithm, whatever setting you have used, and dock the remaining remaining ligand molecule, or what you can say, test ligand molecule. But in our case, we have done both of the things in a same run. Okay, good. So here it is. Well, now one might also wonder as to how do we, you know, how do we compare if the crystallographic pose is similar to the experimental pose. Sorry, if the predicted pose, if it is similar to the crystallographic or experimental pose, that is what I want to ask. Right, how do we say okay, if this pose is more similar to this pose, which pose that our software that has calculated is the most similar to crystallographic pose. Okay, and for that, my friends, you would have to calculate the RMSD between the crystallographic pose and the predicted pose. Okay, so I will just show you where you can find that RMSD. Okay, so for that you might want to go to the folder where you have saved the results. Okay, so here is where you have extracted those results into a folder. I would go to the same folder, and in macromolecules folder you have a single macromolecule for time being, and then open the folder that have results for your NPS. Right, open it. Okay, and open the docking log file. This is there would be two files, docking parameter file, and the remaining one would be docking log files. You can right click and see in the properties, the name is DLG, that stand for docking log file. Okay, so now what you are supposed to do is to open this docking log file into TextPad or any text editor and search for the term RMSD. If you hit next, you would end up in a table that would show that what is the RMSD of your predicted pose as with reference to the crystallographic pose. So this is the RMSD value that you must be looking in. Okay, so as you can see, the best RMSD pose that you have obtained is the lowest RMSD pose that you have obtained is 0.33, and fortunately it is the same pose which has got the highest, or you can say the best score for binding free energy. Okay, and you know these are very ideal results. Okay, so what do this 0.33 mean? 0.33 is the RMSD of your predicted pose and the experimental pose in Armstrong. Okay, so the thing is that you can consider your system is validated if you get RMSD between the predicted pose and the experimental pose below 2 Armstrong value as such. Okay, if you observe the RMSD values below 2 Armstrong, then you can say that your system is validated, right? So this is one of the scientific criteria to check out if your software has predicted the crystallographic pose. Right, if the RMSD between the predicted pose and crystallographic pose is below 2 Armstrong, you can say it has predicted, your software has predicted the experimental pose, and thus your system is validated, and therefore you can rely on the results of the test molecules that you have docked. So this, my friend, is very important, because when you write the paper, your the reviewer might ask as to if you have validated your system, and if indeed you have validated your system, what is the RMSD between the crystallographic pose and the predicted pose as such. Okay, so in that case you might want to show that this is the RMSD between the crystallographic pose and predicted pose, and you might also want to uh, show the superimposed figure. Okay, so you have predicted the right pose. That is all I want to you know show you in this demonstration. Okay, so to revise what we have done, I have shown you how do you download the protein molecule, how do you process the protein molecule, how do you run the molecular docking run. Okay, or how do you proceed for molecular docking, how do you save the results, how do you validate the system, how do you interpret the results, so on and so forth. Okay, so I think this would be enough for today's lecture. I would close this thing. Okay, you don't have to worry for this error, just hit okay, and see you guys in our next video lecture, where I will show you how do we create the complexes for interaction analysis. So see you guys next time.